In this video, we're going to do a quick example where we're computing the dot product. So what I'd like you to do is to consider these two vectors that I've written down here. So this is vector A is 2I hat minus 6j hat, and B is minus I hat plus 2j hat. And sorry, these are j's here. I kind of missed the dots there. All right, so what I'd like you to do is compute A dot B. So, and really, please pause the video here and try to do it on your own before we do it together. Okay, so if you recall, there are two formulas for computing the dot product. One is if you're given magnitude and direction, and the second is if you're given components. Here, when we're given vectors in this form, we can directly read off the components, right? 2 is A sub x, minus 6, and don't forget that minus sign, is A sub y, minus 1 is B sub x, and 2 is B sub y. Again, those minus signs are quite important. All right, since we're given, we can read off these components. The component formula is the one that we want to use, and that's the one that says A dot B is ax bx plus ay by plus az bz. Now you might be wondering, I didn't mention the z components on here. You can always imagine that these vectors are actually plus 0k hat when you don't see a z component explicitly. So really, a sub z and b sub z are just both 0. Whenever you have a two-dimensional vector, which is to say it's only in the x and y direction, you can always think of as the z component as being 0. So this last term is just 0. All right, so let's plug our numbers in. A sub x is 2, b sub x is minus 1, plus a sub y is minus 6, and b sub y, is positive 2. So that's minus 2 minus 12, which is minus 14. And I really want you to notice, what is minus 14? It is a scalar quantity. There is no direction here. So you take the dot product, you take two vectors which have direction, you multiply them together, but then your result is just a scalar quantity that doesn't have any direction. All right, so that's an example in computing the dot product.